10.
How much space does that USB drive have? A lot? More than 16 gigabytes?
Should be in the hundreds.
Okay, alright, cool. Then we can make it. Because I have mine, but they're very small. Where's Chandra? He's coming. I'm like worried about you. Just worried.
Hey.
Oh.
How's it going?
Okay, Zell, you already had, right? Yes. He is not, okay. Remember, I think at the end of that class, you asked me, after Tel also asked me the question during the class to understand this one, right? So let me try to expand a little bit, see if it can help you. So, we can visualize this. This is a vector R.
Right.
That is your actual space or real space to describe the vector. So that is a physically measurable quantity. Here, we use cat R. It is a vector. Also, this is code vector. This is also code vector, but different. This is a vector in the Hilbert space. Behavior, all the behavior follow the property of vector. But it characterizes a state. Or eigenvalue of R. So what does mean eigenvalue? We know that is operator R, position applied to the state. If this eigenvalue vector, so that means the eigenvalue, right? So this R is this.
So the eigenvalue is the real vector.
Yes.
Okay.
And this is just index. Does not mean, okay. If this R is 1, for example, this say 1 cat. It means
Right.
this vector state corresponds to that eigenvalue. Does not mean it is the value 1.
Right.
That makes sense?
Yes.
So now that is okay. I think there's something others. Yes, I think that's enough probably. Index. And then, so now I'm not sure if then you know if this is a R, we know in the position you can either change the R here is from positive negative, right, in the whole space
Right.
orientation. So you have a continuum. Therefore, the eigenvalue is continuum.
Yes.
Therefore, for each one, we have each state. Therefore, we say this state is continuous basis because this is continuous. And then your second question, why are R prime the orthogonal? Right? So let's do that one. So because we know, I don't need the proof, right? This is a permission, right? So according to the theorem 1, we already proved that permission operator, if we have R prime, R hat, the R, that gives us, if applied to here, that is R prime, R, right? This R is this one. And I can get outside, right? So that is R prime, R. And this one can also equal to applied to here, right? After here is equal to, right? Is equal. So that gives us R prime and this inner product, right?
So are you saying that the vector R is a column vector?
If in the matrix representation is column vector, it's column matrix. This is in the continuous basis, is a function, right? So, that answer your question?
Yes.
Yeah, okay. Then you can see, because the right hand side is same, right? So that's equal to 0. You can subtract. Then the right hand side is r minus r prime. I think we did this for the discrete basis, but for continuous, same thing. So if this r equal to 0, there are two possible. If r equal to r prime, then this one. So that gives us this product. There are two choices. If equal to 1, if r, suppose normalize. If these two eigenvectors, eigenvalues are same, or 0. Right? Because if they are not equal, this is not 0,
Right.
then ask this 0. Now it's clear?
Yeah, I think this was very helpful.
Okay, yeah. All right, so I think I know the continuous basis is a little challenge for us to familiar how to understand that what is eigenstates, what is eigenvector, what is the basis. Okay, your homework. Now let's keep continue. We already discussed in the continuous basis how to represent the cat, which is a function. How to represent the operator. In particular, we discussed the momentum operator and the position operator, right? Then now let's also this probability and unit product. Now let's consider the commutator. So, commutator or commutation relation. Let's focus on this very useful, but I use capital R, J, and P, K. The question here, right? So J, K is X component, Y component, Z component. So let's see this, the commutator or commutation relation between the position operator, component position operator, and the momentum operator, right? So how to obtain this? Now, let's, for example, let's just consider the X component. Let's look this one first. Right, so we want to see how much it is. Right, definition is this difference, right? Okay. This is our question. How to do that? Let's first put it in the position representation. Position representation. Okay, in position representation, X operator is X, right? And momentum Px operator is, yes, last time we already mandate, remember? Minus I h bar partial X, right? Okay, so we just put here, then we are going to do. But question here, if we just substitute into this one, you will see this is a partial operator. Without any function, it cannot give us details, right? So we need a function to help us. So we are going to look this. Look this in the position representation, right? So that is the, we see if this commutator is, again, after that maybe a number, maybe an operator applied cat and give us a new cat. So we are going to see the result and then get the information here, right? So now in the position representation is X, X hat is X, and this Px is this one, right? And this one is, right, so the cat in the position representation is a function. And X position operator is also position. The momentum operator is this one, right? So now let's look this. This is to answer this question, right? So now let's continue. So now first is X, okay, minus I h bar partial X, sin X. That is X Px, right? This term. Minus px minus I h bar partial x, x psi x. Right? That is, we extend this one. So now let's do first term. Keep minus I h bar. And this is x partial psi x, partial x, right? And now this one is plus I h bar. Here, this is because this is in form, so we need to do the partial two terms, right? So first one, keep this one, that is 1, right? That is just partial x, right? Psi x. Second one is x in front and do this, so that is plus R h bar, x and partial psi x, right? Then you see these two terms, the first term, third term canceled. So finally we have I h bar. Now let's compare the left-hand side and right-hand side. So left-hand side is this term applied to this one, and the right-hand side is this number multiplied this one. So you can take off this side. This is just a help, a kind of assistant, which can help us. So you can immediately got this. Now xpx is I h bar, right? That gives us the commutator. So they do not commute each other, they give us this relation. That makes sense? You see, like now I can drop this the function psi x because they're the same. So now this one is equal to this one, right? So that is in the partition representation, we obtain that. And this, actually this commutator, this relation does not depend on which representation you are going to take. We always keep this relation. I will give that the property, but it takes time to prove that, so just keep in mind. So now this is for this one. And we can do the same thing, right? So for others, similarly, y and py equal to z and pz all equal to I h bar. Similar thing, we just do the same thing, right? So we have this, if the same components, the position and momentum, the commutator of these two operators give us I h bar. Then now, next, how about this one? Py. Okay, we do the same thing. So this is not py again. If we want to right? So again, in the position representation, we have x py is x minus I h bar partial y. So now I'm going to, again, we are going to use the function to help us. X, actually, I can also use the general. Instead of x here, if I use r, it's also fine. So now let's make general. This either r or x, that is all. Sorry, that. I think that I want to make it small general. So that is r instead of x. So now let's do this x py with psi y. R. Is in the space, and that gives us the position representation is x minus I h bar partial y psi r. Right, so now again we do that. The first one is minus I h bar x partial y psi r minus I h bar partial y x psi r, right? So we keep the first term minus I h bar x partial psi r partial y. Second one. First, they keep the psi r and do the partial derivative with partial x with y is 0, right? Because x, y is independent, so that's only the second term. X partial psi r partial y. And they cancel, right? These two cancel. 0. So if the component is not same, they always equal to 0. Then we have a similarly, all this, I'm going to now get to this in general or in summary. Okay, equal to 0 if G is not equal to K, right? Not same components. So now you can summarize. Summary. The commutator relation between the position operator and this linear momentum operator is I h bar delta I g. If I, sorry, K. Delta G K. Right, so if K equal to the same, then we have I h bar. If not, so that is the commutator or commutation relation between position operator and this momentum operator. Now let's go to, because this is more important, so I'm going to also give you this. In general, the other, commutation relation is if we have x to the nth power and px. That give it, I might give you the result and we are going to prove x n minus 1. Another is x is px to the nth power is 1 bar n px minus 1. So now let's prove. I prove the first one, and you can do the same thing for the second one, right? So the first one, you can use the mathematical way that suppose it is for one of the order, this whole two, then we change or increase one by another power, and then if this whole two, then we can induce, right? So that is the way. So suppose, okay, suppose this one, the kth power, px equal to I h bar according to this k x k minus 1 whole 2. At least the example is k equal to 1, right? We know that k equal to 1, the whole 2. Yes, so that is. Then let's check for k plus 1. Okay, suppose from here, then let's look at the k plus 1 x, the k plus 1 px. Let's look at this one. So that is, if remember, we have the how to deal with the commutator. This is I take k px, right? And then we have I take the k x, the k power in front, and plus remember this, right? So if I have a product AB with C, then the A front is first outside the commutator and B and C, then A with C, but B we go to the back, go to this position. Okay, because this is in this position, right? So this is the back. So the first one, we know this is IH bar, right? Okay, right? Second one, we assume this whole two, right? So that is IH bar It's K, right? Yes, IH bar. What's IH bar? Okay. That is K, K, K minus 1, and we have an X here, right? So they are same, right? But here we have a K, so that means IH bar K plus 1 X to the K's power. And that makes sense. You see here, that is this is N, so this is N. It's a K plus 1, this is K plus 1, and this N minus 1 is K plus 1 minus 1 is K, right? So yes, that holds. Then, so if we define K equal to N minus 1, so we have, okay, X, okay, here, right, XK, so K, XK plus 1 Ex equal to X n, right? Because K equal to n minus 1, so K plus 1 is n. Ex that equal to here IH bar K plus 1. Okay, I think K is n minus 1, right? N minus 1 plus 1 X to K, K is n minus 1, right? So that's IH bar n X n minus 1. Yes, we prove this one. And do the same thing for this one. I will not do that. You can do yourself. So yes, this relation is very important because now next one we are going to prove, or we are going to see how about this function. If we have a function operator, position operator, the commutator relation between the function, which is a function of a position operator, with the momentum operator. How to obtain this? That is very easy. Okay. Let me give you this result, and I'm going to prove. That is just equal to. So you can see here. This one, right? If this position with momentum, that IH1. But if it is a function, that is here is IH1 keep the same. But now this one is df function dx. So proof, because the function operator, it's, we can use the Taylor expansion. Let's use the index k and coefficient k and x. So, okay. So now let's look this. Is the summation k, n k to x, the k's power px. And now we are going to use this one here, right? So I take this coefficient a outside. Since it's addition of this commutator, so that we can take the addition outside, k, and then x, k, px. Now we are going to use this relation, so that is k, IH bar k x to the k minus 1, right? Is this one, if n is k. Okay, so then here I take the IH bar outside, and you can see this is a p px k a k x k, right? When you do the derivative of xk with x, we have a k, and x become k minus 1, right? Is this term? So this. And then that is what? That is function self, right? Your function is this one. So that is IH bar df x and x. Right? Here we have a proof here. Okay. The others as I said, that you can prove yourself those commutator relation will not change if you use the momentum representation, you can use the position representation, or use this matrix representation, and will not change. So that is about the representation continuous basis. We finished. Now the last topic in the chapter 2, I want to finish is this one. We're going to discuss parity operator. The reason why I want to discuss this, because that's related to symmetry. So the parity is inverse symmetry. Then we need to know the symmetry has what kind of behavior. Then later when we deal with the system eigenstates or eigenvector, operator, you will check whether it satisfies this parity. Then you immediately know the eigenstate has some behavior. So definition here. Let's use capital P hat. Apply to R is just make this cat, the R, reverse. That's the definition. So that what means parity? We just try to use this operator to apply this vector, so the vector just reverse from the positive to negative. That is definition. Okay. And then the properties. First one, this parity operator is Hermitian. Hermitian operator. So to prove that, we can do this. If you remember Hermitian, so if we have the Hermitian defined as if this equal to right? Let me see this. If this is Hermitian, so that is that is correct. If right, if this equal, then this equal to Hermitian. Okay, that's a definition Hermitian. So how to do that? Let's check. This one equal to this one, right? So that is equivalent. It's put inside cat or the outside cat is fine. So I'm going to again in this case insert this integral. So I just put integral. It's okay. So that is in the real space. Integral, and this is a bra, right? So that is a complex conjugate R, and this is a P in the position representation, right? That is, and by definition, it will change R from positive to negative, so that is minus R. And now I'm going to replace this minus R by a new R, and it becomes negative, right? That's equivalent to Q. Okay, and then this one is again this is bra. So that is, if I write this with P, right, this minus, it means the parity operator applied to this state, right? Change R from positive to negative. So this equivalent to this, and keep this conjugate again here. So then, you know this integral is nothing but this P remember, right? If this operator in the block, you take outside this, you take this complex conjugate, right? So then you can see here, this one, and this one, that is this. This is the first property. Second one, look about p squared. We do twice, but we haven't. We first go to reverse and come back, right? So that is nothing but the unity operator. Okay. So if unity operator, because the p minus or inverse gives us unity operator, so we have immediately p is also equal to it's inverse. Right, so that's very easy. I think that is because p squared applied equal to p psi minus r, and then do again. This is the first party and makes a change minus r, and do again. Is became minus became r, right? So that is that. So now we have this. Then what do you mean? The p itself equal to it's a complex conjugate and also equal to the inverse. So what is the property of p? Unitary, right? Unitary means this, right? So that is also unitary operator. So very important, very interesting or important in this case, right? So now, number 3, number 4, what is the eigenvalues? Eigenvalues of P. Let's see. Let's look this one. Suppose this is eigenstates of the operator p squared. Then we know that is I, right? What that means? So, what is eigenstates of p squared? Sorry, eigenvalue 1, right? Of p squared is equal to 1. And what is the eigenvalue of p? P plus minus 1, right? So, you can easily understand or know this eigenvalue p. That means if the state has the symmetry, that whatever your change is r from crossly connected, if it is eigenstates of the parity operator, this will correspond to either the eigenvalues plus 1 or eigenvalues minus 1. Only have 2 states, 2 values, right? So now, eigenvalue now number 5, eigenstates or eigenvectors of P. For 1, right? For eigenvalue equal to 1. That means if it is, okay, let me use index, I'm going to use plus 1, so I'm going to use plus to distinguish the eigenstates. So that is eigenstates of operator, parity operator P with eigenvalue plus 1. I'm going to use the plus. That will be eigenvalue 1 multiply itself, right, by eigenvalue problem. If it is, so that is the eigenstate correspond to this one, right? So I use this. Of course, how to find that is another issue. But this give us the eigenstates of the parity operator with eigenvalue plus 1. That is, I'm going to use plus plus. So now, because P, the parity operator here is defined by definition is make this R go to minus R, right? even for his itself, the eigenstates also do the same thing, right? So you compare here, what does it mean? Immediately got this conclusion. This function or this eigenstates correspond to the eigenvalue positive 1. It will not change under the parity. That means you change r from positive to the or inverse, the function will not change. So this behavior we call even eigenstates. So all the states, that is now I'm going to extend. We didn't write down detailed formula or expression of eigenstates, but we know for any giving us the function or the cat, if they follow this, they are even or symmetry. This must be eigenstates of the parity operator which correspond to eigenvalue plus 1, right? So lot, right? We know there are a lot of function has a symmetry, r squared, for example, right? And some other. So that is all that function are eigenstates of this. So that means it's not the only one. You can have all the function if it has this behavior that is eigenstates of this parity operator, this eigenvalue. So now next one is for -1. From -1, I'm going to give to distinguish this eigenstate and this eigenstate. I'm going to say minus. By definition, it's -1 multiplied. Right? Okay, so that is minus. And again, because the parity operator itself, it will reverse r from positive to negative. That will give us minus r, minus r. So they'll compare, because this left-hand side is the same, compare with, then you can find the eigenstates of parity operator P with -1 eigenvalue is R. We call R eigenstates. And also we have R, right? R self. It is if we consider that is a function, then that is follow the art, right? So all the function, if we follow this, they are eigenstates of parity operator P is eigenvalue -1. That is the extent. Now, if this eigenvalues and it is also, okay, I do this Hermitian, right? So we know it's be orthogonal. These two states be orthogonal, right? So now number 6. And orthogonal, or normal, also normal whatever orthogonal is. So, okay, how to prove that? Just look this one. Look this inner product, if orthogonal be equal to 0, right? If not, this is not orthogonal. So now let's look this one. And that equal to, I'm going to keep this plus. And here, inside, I use square because that equal to unity operator, right? That's why unity operator are very useful for us to when we do the analysis. So now p square, as we know, that is unity operator. So I insert p square here between. Then, so one p is go to here, another go to here. Plus. Minus. And this the first one, because we know it's all even, right? This case. So when the p apply this, give us z plus minus r, this equal to, so I just read it. And here, this one gave a minus. So what you have is minus is in the product. Look at the left-hand side. Left-hand side, right side equal just different with minus sign. So only when it goes to 0, otherwise cannot equal, right? So the only one conclusion from this is they are orthogonal. Complete this. Complete side order. This plus minus form the complete side. You have two, right? So what this means complete is it is the eigenstates of the operator which operates the Hermitian theorem. I think 2 we studied before. They will orthogonal, and those eigenstates form this complete set, right? So now the complete set, that means any vector can be spanned in terms of those. Complete also means it's a basic, like a basis vector, right? So any function in space spanned by this specific eigenstate vectors can be have a linear expression or combination of this or superposition. So now that means any, right? So now I'm going to say this any. Then the arbitrary, no any specific function. So anyway, since this form complete, so this linear combination of the set plus the B is a coefficient. Right, that is any function can be extended as a linear combination of this basis vector over superposition principle. So the P, if this parity operator applied to this function, or this cat or operator, that gave us minus R. But in general, it is not eigenstate of this, so it will not equal to plus minus itself. We do not know. But here, apply this equal to apply this, right? But plus minus are the eigenstates of the parity operator. So we have, let me just continue here. The first one, right now here, is minus B. Okay, let's still keep plus and minus R. And the first one is even, so that is A. Second one is odd. Okay, so you see they are not the same, right? You cannot use because the arbitrary function neither even nor are. So when the parity operator apply to this, they will not have either the same with its function itself or negative. No, that is arbitrary. Only the eigenstates of this parity operator has this even and odd behavior. So now, that's fine. We have let's say replace equation 1. Equation 2. So here, this one. So now I'm going to this plus this. Let's see what happens plus. Left side, this plus, then you will see here this term and this term cancel, right? So we have equal to twice of A. So that means, okay, all I rewrite, so now means this even eigenstates of parity operator actually can construct or can be constructed by any arbitrary function of its so I divide to it outside, right? Both sides, right? So that 1 over 2A, one is the summation of any arbitrary function with its parity. That is another way to construct. So in general, okay, we know the eigenstates of a parity operator either even or odd. How to construct? Let's just select arbitrary function. Then we just add these two together. That must be even. So now let's do that. If we have an operator p here, then the p here, so that gives a negative, right? And then p here, negative, that become plus. So that is same thing, right? Okay, then if that is 1, now if we, this one minus this one, so then we have subtract these both, so we can see we have 2b. Then again, we know how to construct this odd eigenstates of arbitrary operator, any arbitrary CAD or function minus this, right? This minus is parity. So we can build up this idea. When we go to the that's the next screen we will discuss continue this quantum mechanics. We will deal with the many particle system, identical path system, and we will know there's a permutation symmetry, and how to construct this, also like this idea. That is this class, how to find this spin with a half, that is a Fermi's and bosons. So that's why I want to give you some of discussion here. Operator, I just do the last one, operator, and then I can finish number 7. Number 8, that is even and operator. Define definition. So if the operator A commute with the parity operator, that means PA equal to AP. So we call this an even operator. That is commute. So if is anti-commute, so that is, remember this one, anti-commute. This is commute. This is anti-commute. That gives us PA net AP. Then we call this the odd operator. When the two operators commute each other, I think I discussed, just mentioned briefly, in chapter 3 we are going to discuss in details. They will form the common eigenstates. I remember I mentioned, right? So, so let's consider for this even, because this is important, even operator. Equal to 0. So what that means? They have okay. They have a common eigenstate such that is A, okay, apply, if this is the eigenstate of A, give us A n, for n, and then the P is also follow this, if I use, we know these are plus minus, right? So here, if they are same, because, ASB, because this eigenstates of the parity operator has either plus or minus. So if they are, if this is a, let me see, if this is a common eigenstate, and this one is eigenstates of A, so that's a different eigenvalue, eigenstate, but also the eigenstates of parity operator, and that gives this, so that means the common eigenstates of is either odd or even, right? Let me cut this one. Either equal to itself, that is even, or that is odd. And in most cases, it is. For example, a Hamiltonian. The Hamiltonian example, Hamiltonian later, let me write down immediately here, but I think you can accept momentum operator plus potential operator, right? So here, this one is even, right? You just make a parity this one. So if, okay, let me do this. If this is a, if this is the even operator Hamiltonian commute with this, if Hamiltonian, this does not depend on R, right? So what R you change the minus plus this. And only same thing here, if there is a central force. So the potential is symmetry. What the plus minus R is the same. So that has this here. Then the eigenstates, right? So if we suppose this is eigenstates of has this is a definite, we call this given definite parity. Definite parity is this one. That means if eigenstates of Hamiltonian either even or odd, they will not be like this arbitrary. So that is the property of the parity. Some of others I think I will not go through, and you can look at this textbook if you are interested. So now let's go to chapter 3. If you remind in the beginning or chapter 1 what we raised our question, right? So remember we said the natural world, if you have a domain, new domain and old domain, remember I plot this one, right? So that is old theory, like classical mechanics or classical physics, only works in this old domain on new theory. We explain all phenomena into this and this. So we are going to establish new theory here, right? Since we found some new phenomena that cannot be explained by the old theory. Then that is our goal, right? That is how to establish quantum mechanics. And in order to do that, if you remember, we said, okay, to build up this one, we need positive. We need the positive because we know all the phenomena are indirectly collected. Not like the old theory, or we can direct collect it like Newton's second law, or he looks at the apple drop down as gravity. He measured or observed several times, he found this the law. But in this quantum, the new phenomena cannot do directly collection. So we have some of indirect, then we need positively, right? Remember we have said that. So we need, if we have postulate, then this postulate can build up the formulas of the quantum mechanics. Quantum mechanics theory. That is what our goal. And then, if the theory is established based on the postulate, so we need to validate it, right? Validated by the experiment or Jacques facts. So if yes, that's good. If no, that is, this theory doesn't work, right? Cannot explain phenomena here. So that is the strategy we are going to establish quantum mechanics. Now we go back to what is conditional postulate. I think I discussed a little bit at the end of chapter 1. We required if the postulates be based on the large or wide range, okay, large range or wide range of observation, right? Observations. And yes, in chapter 1 we introduced like a black body radiation, like a photon electric effect, or like this the Compton effect, and also we have this double slit imaginary experiment. Those give us some of indirect observation to give us some of the new idea which contradict with this, right? But now we need based on those. And then we need the minimum basis set, right? Minimum set. Your postulate cannot be 100 or 1,000. Then that it cannot build up a theory because you condition too much, right? So that's this minimum set of the assumption that can give us or develop that's enough to develop quantum mechanics. Number 3, okay. We can extract from those postulates. We can extract the quantitatively the information for quantum mechanics for system. Information of quantum mechanics system. Right. That is our goal. So if our postulate cannot get this information, that's meaningless, right? Nothing. So that is required. Okay, with this, if you remember those, now we are going to introduce the postulate. What is the postulate? Start from here, and then we are going to build up the quantum mechanics theory. So that is chapter 3. Chapter 3, postulate of quantum mechanics. Okay, let me first brief give this statement of each postulate. Then we can go to some details to explain each one. So first, since we already equipped with the required mass in chapter 2, so when I explain the details, I will speak about some details about this technical work, right? So just focus on physics. So now, first one, postulate 1. Okay, now before that, I want to first, what the questions we want to ask, right? Since those questions to ask ourselves. First, how to describe the state, right? How to describe the quantum state of system. And they should give answer, right? Second one. How to interpret the measured quantities, right? How to interpret the measured, which we can get this physical quantity, measured quantities. Okay, that is enough. See? How to actually this second one, describe the physical quantities, mathematical. In quantum mechanics. Maybe this is a tool, let's get it. Because first one, and then how to interpret this measurable with this. And the numbers 4, what happened when we measure, right? What happened? What will happen? What will happen? Then they measure or during the measurement, let's say before. During the measurement. Number 5, what the outcome, how to interpret or the outcomes. 6, how the states of quantum system evolve. Quantum state. So with this question in mind, we are going to introduce positively, those positively try to answer those questions. And those are important, right? As we say, with those answers, then we can try to extract quantitative information from this positivity. So now we have postulate 1. This is about state, how to describe state or system. Answer the first question, right? How to describe the quantum states. That means now we are dealing with, at microscopic level, we deal with the quantum states and how to describe. So the possibility gives us, okay, the state, okay, state of any physical system is specified part T, right? Instantaneous part T by state vector. Now, chapter 2, the beginning we introduced Hilbert space, and we know in the Hilbert space there are 2 sets of elements. One element is a vector, another element is numbers. So now that is kept in the Hilbert space. See, Why? We have already discussed the property of the vector in the Hilbert space, right? So that now, the reason why we introduce it now, this is characterize the state of the quantum system, or this correct state quantum system. So, why we use this state or vector, we know that gives us a wave particle duality. That is the phenomena which we indirect observe and subtract that information. At least we know in microscopic level, all the particles behave a wave and particle duality, right? So if we use the wave function or if we use the cat, it can characterize those. That is, and of course, as I said, that's beyond the Hilbert space. That is required, and also, actually that's be discussing later in details. But here, what give us interpreted is a probability, right? Related probability and density. Then we require this one must be continuous. You cannot say jump in a certain area. If not continuous, there's nothing the probability to find particle there. Why? No any reason, right? So it must be continuous. And contain all physical, okay. All information of the system. That is to answer the first question, and we require this. It's not an arbitrary vector in the Hilbert space. It's a specific kind of specific state vector or wave vector, such that it can characterize this behavior, can get this or extract all the information of a system, and to give us the information. If we screw up this, give us the probability to find a particle, and that also is inside of the Hilbert space. So all the property in this Hilbert space is satisfied. So that is the first. Postulate to answer the first question. Then the postulate 2. Postulate 2 to answer the second question. Yeah. How to describe physical quantities in mathematically in quantum mechanics? That gives us the relation of observables, which measurable, right? Observables like momentum, energy, position, and the relation with operator. See, in chapter 2, we introduce operator. The reason why in quantum mechanics we need the operator, so we discuss the behavior operator, the some property of operator, different type of operator discuss a lot. Now you will see why, because they have connection with these two. So the statement says, okay, so every physical measurable quantity could be correspond to one of the operators. That is the sentence. Every physical measurable okay. For example, I use A. Now I didn't use fact here, so that is a measurable physical quantity. Okay, we call this observables. So when we say observables means this. For every there are three spots. Linear Hermitian. So now you know what is Hermitian, right? Hermitian operator A. That is the relation between this. So now you can see here, the operator is not an arbitrary operator. The physical quantity which is observable or measurable correspond to that physical quantity. They postulate to say there must be correspond to an operator. This operator is Hermitian, not any others. Okay, so that is the second answer to the question how to describe the physical quantity mathematically in quantum mechanics, Hermitian operator. So if since we introduced Hermitian operator, you know. Okay, try to find the relation between this and this. So for Hermitian operator, we already know. Right, this eigenfunction of Hermitian operator, and this is from I just keep here, right? If you remember this, and here, what is the conclusion for this? Real, right? That is why the physical quantity all are real. So the corresponding to this physical quantity operators to be Hermitian. Others, the eigenvalue is not real. So that is case, and that is observable. That means here, when we observe the numbers, values, energies, or that is nothing but the eigenvalue of the corresponding Hermitian operator. And the states, this is the eigenstate, right? Eigenstate of this operator A, and we know this, these states, first, they are orthonormal. I just use the discrete expression that the continuous. You use delta, Dirac delta function, right? It's orthogonal. Orthonormal. And complete. Complete means. See, I always use this. So that means immediately know this implied we already know. Okay, that is this postulate 2 to give us that, and of course here, this must be physically, has a physical, right? Physical. Required. And what this means physically required later in details we will discuss, like this probability, given probabilities we continue up to second the order of derivative. So when we extend the detailed discussion, we will give us details. So now that is second postulate. The third one is a little challenge, but let's try to answer. Right, measure, the interpreted measurement, right? So that is a postulate 3. That gives us the relation or interpret the measurement and eigenvalues. operator. But now, when we say operator, that is already discussed in positive loop 2, which is permission. So, okay. That is similar. There are several key concepts here. So, the measurement, when we have the measurement, right? That's it. The measurement. If we want measurement of an observable, okay, observable, A, right? I use A, not A hat. This if with the measurement of this observable A can be represented in terms of mathematics, right? Represented formally by I by the operator, right? By the if I use A hat, this operator corresponds to observer A acts on the state hat. So that is the explanation what happens when we measure. When we measure, actually is nothing but the operator itself acts on this cat. And in chapter 2 we know the operator acts on the cats, give us a new cat, right? So that is okay. That is the interpret what happened and then the result. Okay. So the only result from this measurement, the only possible result. Okay. It is maybe possible. It is only the possible result of such measurement, okay, this is the key here. One of the eigenvalue. Okay, so mathematically now I'm going to write here. That is measurement and that is before, right? Before measurement or just before we have state. That's from the states. We are going to do this. Initially we have states, so now I'm going to measure. So what happened? That is operator act on this, and the result is one of the eigenvalues. So that result, your measurement result, must be among this one of this value, and go to one of the eigenstates. That is interesting, right? So what happened? Yes, you change the states from initial, that is initial states, and operator act on that. We know if you change the new states, these new states will go to where it must be one of the eigenstates, not arbitrary. That is the postulate. Okay, sorry. I think we already 5 minutes after that. So let's stop here and try to continue. So that measurement is a key. Actually, this is what we can get the output. The output from here to check just So we need to understand what is the output from measurement, what that means. Okay, I just remind you, homework 2 is due now next Monday. I hope you can finish. Then I am going to read and turn to on the next Wednesday, and also the midterm exam, right? Next Wednesday. Yes.
And
So
the
midterm, yes.
will be due